Hey, welcome back. Today we talk about this thing. This is a belt sander, disc sander combination machine. 25mm wide belt, 762mm long. I think in the US they are sold as a 1x30 belt sander. I saw versions of this without the belt sander, just a motor with this belt sander attachment here. This one has a disc sander on the other side, which I'm not very keen of. I have no real use for a disc sander, but we'll see. What I'm interested in is the belt sander attachment. I had this thing now for 2 or 3 weeks, and I already used the heck out of the belt sander. I have no idea how I was working in here without a belt sander. Deburring, when I did the fabrication work on my new weld cart, I used the belt sander a lot for chamfering the angle irons, removing mill scale from the ends of the angle iron for welding, deburring, regrinding the tungstens for my TIG welder, just everything that I do not want to do on my bench grinder. Deburring parts on a bench grinder is very cringy. Rounding off the ends of parts, just things like that. I have a 80 grit zirconia aluminum oxide belt on it. This works very well, cuts relatively freely. I have also coarse and finer belts, but I think I will stick with the 80 grit. Seems like a good compromise for my work. Has a ginormous 250 watt motor. And I think the motor is the only part on this thing that's made out of steel, except for some smaller attachments like the belt guide here. But it works. Even the dust collection back here works, kinda. If you hook up the shop vac, it works. My gripe is the table here. This is die cast aluminium, and it has this belt sander or white belt sander finish on it. It's not very even. This table has a 0.5mm ditch in the center, which is quite a lot. If I want to square up parts with this is not really acceptable. And it's so soft, if you push something with a slight burr over it that's harder than, say, a piece of butter, it will scratch the table. I ordered a plasma cut disc of steel, about the same size, 8mm thick. This is just cold rolled plate. This will need some finishing. This is really butt ugly, and it has this big old curve. This is the pierce point where the plasma cutter pierced the material. So that's the table, and also this. Let's take this table off. Okay, as you can see, there is not much material in this table. This is super lightweight. Not a lot, really no substance there. It has an end stop, so you can set your 0 against this belt guide back here. The belt guide is the next problem. As you can see, if you push up a bit against it, it bends. This table can be adjusted on an angle, so you can grind bevels. I have no interest in that, so I will remove this belt guide back here. The housing of this belt grinding attachment is die cast aluminium, and this belt guide is just screwed up again on it. So yeah, that's the original belt guide. The problem is when you bend the table under load, or you bend this by pushing or shoving your work against it, you're not going to get a square result anymore. So this seems to be a recurring topic in my shop. Robin Renzetti, of course, has a very good solution for this. He took a high-speed steel blank, which is nice because it's hard. It will not wear, it will not be abraded anytime soon by the back of the belt. This gives a very nice belt guide. This is a trapezoidal high-speed steel blank, so I will have to grind it parallel. And I will not mount this high-speed steel blank, this belt guide, to the housing anymore. It will be mounted to the table itself. So if the table deflects under load, no matter what we do, it stays square. And due to the fact that the high-speed steel blank here is about twice the thickness of the original guide, it's also stiffer against against bending in itself. And let's take this cover here off. I have to find a better solution for this cover too. I do not want to run this grinder without the cover because this is integral to the dust collection, and really I do not want belt grinder without dust collection. It's already messy enough in here. It's a 3-roll grinder, all plastic wheels. And yeah, you can see there is a lot of grinding dust in there. I used it a lot. And there is some reasonable run out on this wheel. I might try to true it up, or I will just take a piece of aluminium and turn a new one. Maybe the added inertia of a heavier wheel will also make this thing run a little bit smoother. Right now this is quite noisy. And in case you wonder why I have 2 of these plates here, a friend of mine has exactly the same, so I will make 2 sets of these parts. He might enjoy it. Cleaning up the plasma cut discs on the lathe, holding it on a magnetic chuck, and I put a small center drill in the center of this disc, and I'm supporting it with the live center because I do not want to take any chances of shifting this large plate during a heavy cut, fairly heavy cut, off the magnetic chuck and doing some major damage. Running at 200 RPM and a feed of 0.06 millimeters per revolution. So for my, this is fairly large for me. I'm not concerned about the faces at the moment, I'm just cleaning up the plasma cut OD. After I did the welding, there was a little bracket that gets welded on this disc. It will not be flat anymore anyway. There we go. Chamfer both sides of the disc. There we go. One disc, 148 millimeter. Let's get the tailstock out of the way and unclamp it. There we go. Boop. One steel disc, reasonable finish. One to go. I stoned the back side of this plate so I do not scratch up my magnetic chuck like crazy. Bring in and mark the center with a Sharpie with a permanent felt marker. Finding my center roughly and turning on the magnet. There we go. Okay, ready to go. Quick look at the drawing. Bottom view with the tab that bolts against the belt sander's housing. This is the 148 millimeter disc that we just machined, and now we need to mill this cutout here for both the belt to go in and out and the belt guide that bolts onto these two M6 threads, which I forgot to dimension here. I'm going to cut this cutout and the holes in both parts at the same time because I do not want to do the setup twice. I have a piece of sacrificial aluminum here in the vise. I use this as a kind of a fixture plate. It has a few threads in it, but that doesn't matter for this application now. Both parts go on here. Now I need to align them to each other. Precision ground magnets do this job very well. This large one is a bit heavy, so it wants to tip over. 2 and 3. That aligns the two discs quite nice to each other. Now we double check here on the edges. So this bigger magnet is quite annoying. Okay, nicely aligned to each other. Now we can use some large clamps, some heavy clamps to hold this together and against the fixture plate. We can take the magnets off. Add 2 more clamps for good measure. With the clamps out here on the OD of the parts, we cannot use an indicator to dial this part in, but we can use an edge finder. Pick off both sides, find the center, pick off both ends in this direction, find the center, and it's almost good as sweeping it with a dial test indicator. Picked up the first side, moving over, not moving the Y direction. If you move them up Y direction, you're wasting time. There we go, dropping down. Picked up the second side, now moving to the center of the picked up dimension. There we go, that's center. Now we do the same in the Y direction. I hope my travel, I think I cannot travel. Okay, we cannot pick up the center in this direction, so we will just pick up this edge here, this high spot here, and go from there. Okay, I think I'm going with a corncob style roughing end mill. This is a high-speed steel end mill, so we're not going to run it at crazy speeds. Got my cutout, 0.5 millimeters allowance in each direction, so now we can change to a 6 millimeter standard finishing end mill and clean up those walls. Would be okay to leave them with the roughing end mill finish, but no, we're not going to do that. Off camera I made these two parts. Nothing special, it's just 12mm cold rolled material and a few slots milled in it. These two are the slots that match up with the hole pattern and the table, like this. Can remove to the back. And the center slot is where I will silver braze the high-speed steel blank. High-speed steel, being what it is, of course will keep its hardness when silver soldered or silver brazed. It's not going to get soft by this treatment. I also milled a step in here. And the step is here to act as a relief down here between the high-speed steel blank and the surface, which rests later up against the bottom of the table. And this relief is there, so I can machine the surface here through to the high-speed steel blank. If there is any movement from silver soldering, which I do not really expect, but it's good to keep the options open. And this is not going to be a surface grinder in the end anyway, but it should be at least half decent square to each other. These parts are right off the mill. I just deburred them a little bit with the file so I do not cut myself while handling them. Final deburring will done in the end. Next I will surface grind these trapezoidal high-speed steel blades. They are square here and square here, but those two surfaces here and here are not parallel. So we'll put them this way on the grinder and clean them up. I already ground the taper out of the trapezoidal shape out of the high-speed steel blanks. Didn't clean them up completely, there is a little bit left here, but this side gets silver soldered into the block, and this side is where the belt runs over. So this has a blanchard ground finish as usual. So we're going to clean this up and give it a lengthwise grind with a fine dressed wheel. We're only taking off a few microns. It took me 35 micron to grind out all the marks from the blanchard grind. There we go. Looks like a half decent finish to me. This side is a bit rougher. Didn't redress the wheel, but as I said, this side is not a functional surface. Next step will be to take these high-speed steel blanks, orient them correctly like this, and silver solder them in. For silver soldering, I want to clamp them together with vice grips. But the problem is when you clamp a silver brazing joint completely tight, there is no way you get your silver solder over the whole surface between the gap, and that's what gives you the strength. So the way I learned to do it during apprenticeship, we took a center punch, big old center punch, and we put 4 dimples in each corner. In each corner of the surface you're brazing or soldering. This gives you about 0.05 to 0.1 millimeters of gap. That's where your silver solder can flow. Same on this one. There we go. Now we can clamp it shut, but we still have a gap for the solder to go. Of course, we have to put the flux between those two parts before we clamp it together. One thing I was surprised, the high-speed steel blank did basically not move when I removed almost 1 millimeter of material from one side. It's still straight as an arrow. This is new old stock made in the GDR, German Democratic Republic, high-speed steel. And that's the flux I'm using. This is Fontargen F300H Ultra NT. This is a high-temperature silver solder or a high-temperature flux for steel, copper, tungsten, tungsten carbide. The stuff gets very crumbly over time like this. You can take some distilled water and give some life back into it. Usually this stuff is always dried up. That's normal. Tom Lipton showed silver brazing the other day. And as he said, do not put flux where you do not want silver solder in the end. So we spread it out nice and even. Take our high-speed steel. Take our calipers that are preset to 20 millimeters. Place it here. And we take our prepared clamp. Clamp it together. Double check it. Good. Remove the flux where we don't want it. Okay, ready for brazing. Got my 4 to 6 millimeter rosebud torch here in the small Gregerson torch. And I'm using this stuff, Jet A. It's a 1 millimeter diameter silver solder with 30% silver in it. Yeah, I overheated this one over here. The solder flowed and then I overheated it and I got this ugly dingleberry here. This will probably clean up. This one really flowed very nicely. But it's all right now crazy hot. Okay, I beat blasted the parts and they come out nice. The solder joint is relatively decent. It's okay. I got some silver here and here. It wicked through to the other side. Should be a sound joint. I don't worry. The nice thing about silver soldering compared to welding is that the distortion you get from silver soldering is very, very small. I'm probably not going to regrind this flat surface here. It has a tiny bow in the middle. So these are the second one is already, I put it already together with the table. Here is already in place. I cannot bolt it yet to the grinder because the mounting bracket to bolt the table to it is missing yet. But I have already the belt guide here in place. This is looking very good. The idea behind this design is really good. As I said, it's not my design. When you put pressure against the belt by grinding here, and you bend the table mounting on the grinder, the whole table shifts back. The belt guide here is flexing with it. So within reason, your grind will stay kind of squarish because you will still get the belt is elastic and wants to pull forward and wants to roll over the edge, but overall it's going to stay very straight, especially if you put a lot of load on here and we bend it forward, then it's looking very good. And it stays in full contact and the belt is running here over the edge. I have to round over these edges here and down here on the high-speed steel belt guide, so I do not tear up the backside of the belts. But that's the basic idea behind this. Next will be to fabricate the bracket that mounts to the grinder and weld it in place. I'm machining the tabs that get welded to the bottom of the table. These are milled out of 6 millimeter sheet metal, cold rolled plate, and outside dimensions are already milled. Didn't show that. That's not very exciting. This is also not very exciting, but I need to fill the video. Cutting the slot, pre-drilling the end, drilling both before I change to an end mill. Using a parallel as the rough stop here. The location of this part, of the slot in the part is not super critical. 0.1 millimeter left or right will not matter at all. The slot is way too long anyway. Stub length 8mm 4-flute carbide end mill. I'm opening up the pre-drilled holes with the 8mm end mill before I cut the slot. I dropped down 1mm increments and then until I was all the way through. And then I stepped over 0.1 millimeters on each side to clean up the sidewalls. If you're just plunging down full slotting cut, the sidewalls of a slot never get very nice. Deburring the slot with a chamfer mill, running the chamfer mill at center of the slot. Center to center of the end diameters. So I just have to drop down, move end to end, and get a chamfer all the way around that way. There we go. I could do that with die grinder and the burr too, but this is faster and gives a more consistent result. I'm pretty much ready to weld, but I need to clean up the area where I'm going to put the weld. I got a new toy in the shop. This is a flex shaft motor unit, a pendant motor, like the British say. This consists of a 450 watt motor that's hanging back here with a flexible shaft going to a handpiece. This is like a Dremel on steroids. This is a quite heavy duty handpiece. This goes up to 6mm collets, almost quarter inch. And for the most part it replaced my 90 air grinder. I used to use this with this 3M Rolock pad for small grinding jobs, but this is awful loud. Takes a ton of air and it has no torque at lower speeds. This thing, on the other hand, has tremendous torque at low speed. And with the foot controller down there, you have a lot of control. This is really cool. Fordom is a very common manufacturer of these units. Fiat. This is a Haspa, also made in Germany. Got this used off eBay. They're rather expensive if you buy them new. There we go. This thing has this really has a good bite. Cleans off the scaling from the rolled plate without a problem. Even with a very clogged up and dull sanding pad like this. Seems like I'm collecting hand grinders at the moment. I have the 60,000 RPM air die grinder, I have the Haspa flex shaft, I have my small Proxxon electric die grinder, I have the large 90 air die grinder, I have a large electric die grinder. It seems like this has no end. I figured the alignment already out and I have a magnet in here. A gauge block here, that's my spacing in this direction, and in this direction I put a screw in here and a stack of gauge blocks right up against it, and then I can push my part in here. I had to mill a little bit clearance back here, so we will see later why. And now the part is pretty decently aligned. Now I can clamp it. Okay, the large Bessie clamp does the trick. Large. Yeah, I'm using gauge blocks for weld setup. These are beta gauge blocks that have not much precision left, but for welding they are still okay-ish. Wiping it down with some acetone. For my standards, this is a pretty decent weld. I think I have some spots here and 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 arc strike here and here that shouldn't be there. Not sure yet what I'm going to do about the tabletop. I might face it. We'll see. Depends on how bad it is flatness wise. So after face milling the front, the tabletop, I flipped it around and I'm also milling the mounting surface where the belt guide bolts to. So everything is in the end square, even if I have significant distortion from welding. This thing bowed by roughly 1 millimeter by the huge amount of weld metal and heat input I put into it. So this plate potato chipped seriously on me. But that's not a problem. There's a lot of material on it and I can machine it true and square in every aspect that I need. So 60 millimeter face mill running at 1000 RPM, taking 0.2 millimeter cuts. This setup is not the most sturdy, but it's fast to set up. This is just a tooling plate, a large parallel in the vise, and 2 clamps holding the table with the machine surface down onto the plate. Here you can see how uneven it cleans up. Here we have a fairly deep cut, 0.6 millimeters already, and here we have still the scaling of the plate. As I said, not a big deal. There we go. Now cleaned up completely. And we can tear down the setup too. So the belt, back plate and mounting bracket need a little bit of squaring up. This stayed straight, but the angle between the high-speed steel plate here and my mounting bracket here, this is not 100% perfect. It deviates about 100 micron over 50 millimeters. So I dropped this piece here in the vise onto parallels with the face of the high-speed steel blank, like this. Press down, and I clamp it. And now I can side mill this bracket square to the underside of this high-speed steel blank. Let's see if we clear the high-speed steel blank. There we go. That took 0.6 millimeters to square this up. This was not only tilted this way, not tipped over like this, but it was also like this, turned counterclockwise about 0.6 millimeters over the whole length. So now this is square and parallel and whatnot to every aspect of this high-speed steel blank. So I took out the upper guide roller of the belt grinder, and as you can see, it's on its axle and it's free spinning because it has 2 ball bearings in it. The bearings feel okay-ish, but the runout was all over the shop. This ran out almost 1 millimeter on top. I wanted to turn it down on the lathe, but I couldn't figure out a very good way to hold it on the shaft, have it run out its own bearings, and turn down the OD. So I decided to go to the tool and cutter grinder, hold it on the shaft so the wheel can spin freely. And I use my cordless drill with a plastic disc in here that has an O-ring and rubber O-ring on it. And I use this to drive the roller. I just rest it here on my dressing diamond, press it up against the wheel here, and let it spin. Grinding wheel spins also, of course, and then I'm just cylindrical grinding this wheel. All 3 wheels on this belt grinder have a crown. You need the crown so the belt does track properly. To my knowledge, 1 wheel with a crown is enough. This grinder has 3 wheels with a crown, so I will try to grind this to a full cylindrical shape. These are solid Delrin, so shouldn't be a problem to reduce it in diameter. Okay, I destroyed the original drive wheel, put it in a lathe on a mandrel, and I turned the OD through, and at some point it catched and it destroyed itself. Which was a little bit expected because it's all very thin and the Delrin they used is crazy brittle. I don't know Delrin to be that brittle. Sounds almost like a blend with a different plastic. I'm not sure. So I found a piece of phenolic, linen reinforced phenolic, which is quite heavy. The right thickness and the right size, so I'm going to make a new wheel. So we'll basically bandsaw out a disc out of this material. I'm using the linen reinforced phenolic here because it's very tough material. It's a little bit heavier than Delrin, especially for this part is made with massive material reduction here, so it can be injection molded. You cannot injection mold a massive part. It would shrink beyond any usability. So that's the reason why these are so thin-walled and ripped. And of course, because it's cheaper, because you don't need as much plastic. But in my case, I can use a massive chunk of material. This will give additional mass, more inertia once it's rotating, and hopefully stabilize everything a little bit. So bandsaw this out, kind of squarish, octagon shape, whatever. Okay, over at the lathe, I put a large center drill in the rough sawn disc, and I'm just pressing it against the half-opened 6-jaw with a live center. Let's call it pressure turning. With a very safe method of turning a rough sawn blank into a round disc, with the tailstock in the center drill here, it cannot fly out. It's absolutely impossible. You would have to shear off the center, the tip of your life center, which will not happen. The only thing that can happen is that the disc spins against the chuck. So the chuck keeps spinning, but the blank stands still. That can happen if you take too deep of a cut. Phenolic makes an awful mess, so we definitely are going to use dust extraction here. Now we can change to the different chuck jaws, grab it on the OD, take a facing cut, drill and ream it to 14 millimeters. The original one has a D-shaped bore, which is in my mind not necessary. They did this to transfer the torque, but this grinder has 250 watt. That's equates to very little torque, and the friction between the face of this and the shoulder of the shaft applied by the fastener that holds it all together, that's way sufficient. I'm not worried of any kind here. Now we take a very minor facing cut. Now we can drill it out to 14 millimeters, drill and ream it. I'm running a boring bar through there, so it runs really nice and true. A drill doesn't do that. A drill will wander off course the moment you give it a chance, but a boring bar will create its own true path. And I'm going to bore this to 13.8 millimeter and then ream it to 14. Flip it around, take a tiny facing path. I'm not too worried about cleaning it up completely. I just want it to be reasonably balanced. One new wheel for belt grinder. Looks like a wood wheel. Okay, I think I will leave it here for now. I put the phenolic drive wheel back on the motor. I had to put a crown on all of the wheels. This frame is too flexible to have the belt track by only one crowned pulley, so I had to put a crown on all three wheels, but more precise than the original ones. It's just a 3-degree bevel, about a quarter of the width of the wheel on each side, and that's the crown. And that's good enough. All is running nice and true now. It's more quiet than before. I ditched the spring of the belt tensioner back here. The way I'm changing belts now is I locked it in the most outward precision, and then I just forced the belt over the edge of the idler wheel, and that tensions the belt to a nice degree. The frame has enough flex, so this works. The table is in place with the high-speed steel belt guide. This is really cool. Let me put the guard back on so I can use dust extraction, and we will grind something. These are all the modifications that I'm going to do for now. In the future I want to put a diamond wheel on the other side. I already removed the disc grinder here. I will put a diamond wheel on here and an adjustable table. Basically this table just out of steel, so it doesn't this is very grabby when you try to push something out of steel over it. And I want to use this side to resharpen carbide tooling. I need to turn an adapter sleeve for this. This is a bit... Okay, I have a piece of tool steel here, which has two factory edges here and is sawn off on the end. This is not very square. Okay, I have the part in the vise and I have a precision square here, a blade square, a knife edge, and let's check for a light gap. There is a really tiny gap over here. This is 10 micron shim stock. This barely goes in. This is 40 micron. This doesn't go in. A length of 50 millimeters, and it's square within maybe 20 microns, and that's off a belt sander. I guess that's okay-ish for my purposes. I'm very happy with the modifications. I will revisit this project at a later time when I get a diamond wheel for it. Until then, I will just use it. It already has proven to be useful in my shop in an unmodified state, and now with the precision belt plate here, it will be even more valuable, especially grinding radii and edges of parts and stuff like that. I will use the heck out of this, and you will see it in future videos definitely. So, thank you all for watching and see you next time.